Right now, if I have a certain pathology, or if I have a stroke, or a specific problem in the patient's body, this pathology or the existing issue can affect the movement of the molecules present. For example, normally there is water between the cells, like in the extracellular space, which moves freely without any issues between all the cells. This allows for freedom of movement. However, if we have a specific pathology, this pathology has affected the interaction of the sodium-potassium pump, for instance, causing a problem in the cell membrane. This leads to an increase in the water content inside the cells and results in a restriction of movement. In this case, we have a specific pathology that has caused a problem, which has led to restrictions in the movement of water and the molecules present in this tissue. In this case, the natural movement remained in a state of normal movement or diffusion. What happened is that a certain lesion affected it in one way or another, causing a restriction in the movement. When there is a sequence in MRI, this sequence starts to indicate that when there is pathology or something that maximizes the difference between whether the water molecule or the protons present in the water molecule are restricted in movement, you will benefit from this because it will help me in diagnosis significantly. If I can say that the protons are restricted in their movement, then I am dealing with a lesion or a stroke or a specific pathology that has led to hazard restrictions in proton movement. I concluded that the signal I am receiving is a result of hazard restrictions. In cases where there are no restrictions and movement is normal, then it is normal. This is important because some patients may present with a certain signal in their brain, and there will definitely be a signal like T2 that is illuminated. Prison is not easy, it's hard. Strong two types of long evolution piece. For example, I have a brain issue, or there is a specific lesion, or there is a certain problem with water that you are suspicious about. As a result, this pathology has some fluid. This discussion revolves around the crucial and widely recognized elements, as well as the series of steps and processes that are essential and heavily relied upon when making a diagnosis. These components are fundamental in ensuring accurate and effective diagnostic. The idea of diffusion, of course, as you know, what do you do when you suspect a stroke? They tell you to perform a diffusion protocol, and you ask the technician if diffusion was done or not, and it shows you an image at the environment saying diffusion at 500 or 800 or 1000, I'll be 800, I'll be 1800. The ADC image is used in the diagnostic process to determine whether there is a stroke or not. The whole idea revolves around diffusion. As I mentioned, if I have a certain pathology, this pathology affects the movement of water or protons from water molecules inside the cells or within the tissue, causing restricted movement instead of free movement. This means that, as I said, there is more movement outside the cell. If I have an issue like a tumor or an abscess, or for example in a stroke, it leads to a change in what is called the sodium-potassium pump, which is responsible for determining the concentration gradient of sodium and potassium between inside and outside the cell. If there is a concentration inside the cell, water will start to enter from the outside to the inside, increasing the influx into the cell and creating a concentration for movement within the cell, allowing it to move freely, whereas before it was outside and moving freely. Is that clear? So, the presence of pathology affects the existence of a water problem or a gene or anything that leads to the burning of the movement of protons within the molecular water. From here, the idea arose to create a specific sequence that illustrates this burning that occurred in the movement of protons. If I have a restriction, it gives me a certain signal. If there are no restrictions, it gives me another opposite signal. In this case, you assert that there is a problem that caused the restrictions. Therefore, if there are no restrictions, then there is no problem. And if there are restrictions, then there is a problem. The whole idea is that if I take, for example, a cup of water, and if I observe any molecule inside the cup of water, you will find that this molecule represents that it can move in any way, thus representing isotropic diffusion, meaning it can move in any direction. So the probability of it moving in X, Y, and Z is all the same. But if it moves in a certain direction relative to the environment, this is called anisotropic, and it depends on the diffusion tensor imaging sequence, which is tractography. However, today we are talking about regular diffusion, which is the sequence I want to mention. In a typical MRI procedure, in my regular spin echo sequence, you apply a 90-degree pulse followed by a 180-degree pulse, which is a common technique in MRI. Now, if you are taking a T2 image, the fluid appears bright, for example, which is a common occurrence in MRI scans. There is no problem. Okay, if I just say I have a specific ligand or an existing problem, this problem appeared in the brain, for example, here, and it showed a bright color. I want to know if this could be normal fluid or not. Is there a problem or not? Is there pathology or not? What is the idea here? It tells you that you are now performing a certain sequence that maximizes the effect of diffusion and molecules. What does that mean? It means that now if I am imaging, for example, in the brain, I have what we thought was a frequency encoded ingredient and a phase encoded ingredient. If I take a square, which I call a voxel, and talk about 3 dimensions, this square contains a group of protons inside the pixel or voxel. If I take another square, let's say we perform maximization on the first square to enlarge it, the protons inside are moving in free motion, meaning there is no pathology present. They are all moving in an extracellular manner without any issues. For instance, I see a very bright signal with no problems. In the T2 image, for example, there is a lesion or a specific pathology that is causing a restriction to the movement of the protons present, but there is fluid content. This will appear bright, and this will also appear bright. Why is that? You have 90 degrees and 108 degrees here. Your main factor is your T2 constant. But I have one number for restricted diffusion and another for free motion of the water particles. So I want something to differentiate between 1 and 2. You are applying the up-life frequency encoding gradient and phase encoding gradient, and you have the slice selection gradient. The water molecules or free particles or protons can move in the X, Y, and Z directions. So, what is the purpose of these 3 gradients? One of them is used for slice selection in the Z direction, for example, and we said that is Gx. One of them works on the phase encoding gradient, meaning in Y, and the other is the frequency encoding gradient in X. So these three directions allow you to apply the gradient in X, Y, and Z. So what will this application do? What is its benefit in simple terms? The X, Y, and Z are fine, but what will I do with the apply? I mean, if I do it. The protons that are present inside the voxel move normally. If you are in the normal state, you are accepting a frequency-encoded gradient and a phase-encoded gradient, and the slice selection gradient. These gradients are not sufficient to maximize the difference between lesion number 1 and lesion number 2 in the diffusion of protons. You need something stronger. You need to apply a gradient with a higher magnitude and a longer time to maximize that difference. So why would a gradient do anything? Imagine with me that you are applying the gradient in the X direction. The protons are moving because you have applied the gradient here. And these protons are moving as a result of you applying a high magnitude gradient, meaning a strong gradient, which means the difference between this point and that point is high in the strength of this gradient, although the protons are moving in free motion. This means that this proton will be affected by a force different from that of this proton. Although they are in the same voxel, they move easily in free motion. This movement will lead to a situation where, when you use a 180-degree pulse and apply the protons, the result of using this gradient will occur at a different time, causing a loss in the signal. You get two halves in the signal due to the application of this gradient while they are in motion, applying a strong gradient for a long time. Now, if I have both moving, and if I have these protons stationary, the effect of the gradient on them will be different. The gradient will not create this effect in the signal when you apply the gradient to them while they are not moving. This means that the movement of these protons makes them more susceptible or increases the probability of moving from one point on the gradient to another. This will make the phase encoding more effective and create a signal. Unlike when your protons are stationary in the same place, you will find that the protons that are restricted in a pathological area or in a lesion create a restriction to their movement, which will give you a signal that is in phase, providing you with higher signal intensity. What happens in free motion is that essentially, if you have an abnormality or lesion here, this abnormality creates a restriction for the diffusion or movement of protons, and then you apply the X gradient in all three directions, X, Y, and Z. With high magnitude and high time, protons in free motion move quickly and will experience a loss in the signal, while protons that are restricted in their diffusion will have a signal that is more bright compared to the signal of those moving freely. This is what I do in diffusion. I apply a 90-degree pulse and then a 180-degree pulse, along with the first gradient, the second gradient, and the third gradient, which is for slice selection. In a significant manner, protons in free motion move at a rapid pace and will experience a loss in the signal, while protons that are restricted in their diffusion will have a signal that is more bright in comparison to others. This is what I do in diffusion. I apply a 90-degree pulse and then a 180-degree pulse, along with the first gradient, the second gradient, and the third gradient, which is for slice selection. The first gradient and the second gradient. This is slice selection. This is phase encoding, and this is frequency encoding. It tells you what to do. It tells you to apply a gradient here, and a gradient here, a gradient here, and a gradient here, a gradient here, in every direction in the X, Y, and Z axis. The directions don't matter to me before 108 and after 180. Why? It tells you that the gradient you will apply, which is before and after, is with the stationary protons, The gradient before this compensates for it, meaning if you perform diffusion, the other one will gather, so it doesn't matter. But who will be affected? Who will be more susceptible to the effect? The protons that are moving. The applying of the gradient accelerates their diffusion and affects their diffusion and precision frequency. So, one proton leads while another lags behind. And when you take the signal from it, you find it weak, resulting in a loss of its signal. This discussion is about the gradient strength in the X, Y, and Z axis. It mentions why we refer to it as stepping, magnitude, and time. What does time mean? It refers to the duration for which you are running the gradient, meaning the time you are operating the gradient. The gradient magnitude and gradient time are both linked by an equation called the p-value. The p-value is a set of parameters that describe the gradient, including its strength and duration. The higher the p-value, the greater the strength of your gradient and the longer its duration. That's why if you take an image with a p-value of 0, which is similar to a T2 image at 500 or 1000, the more you increase it. Everything that increases or maximizes the difference in signal intensity between the stationary protons and the free motion protons, well, if this is the meaning of the word p-value, then I have there is a relationship between p-value and signal intensity. If I have free motion protons, protons that are moving freely without anything stopping them, the signal intensity decreases as the p-value increases. As the gradient magnitude increases, the gradient time also increases, which means it will be more affected by the gradient. Therefore, its signal intensity will be normal. This relationship, known as the exponential relationship, indicates that if you take the signal intensity at any p-value, it is equal to the signal intensity at p0 multiplied by e raised to the power of minus b times d. This is an exponential relationship that we don't need to delve into too deeply. What I want you to understand is that the signal intensity at any p-value you want is equal to the signal intensity at p0, which is like your T2 image sequence, multiplied by e raised to the power of minus p, which is our p-value, times d, which is the apparent diffusion coefficient, ADC. You always get an image, or the technician provides you with an image, and this image is, for example, 500 at 1000, 500 p1000, or 800, for example, and it tells you that it calculated the ADC. What is this ADC? The D in ADC is for equation, meaning if you have P at 800 and P at 0, you can derive the ADC from it, as ADC is considered a calculated image. Based on the ratio between your signal or signal intensity at, for example, p-value 1000 and the signal intensity at p-value 0, which is 2, the signal intensity at two different p-values, allows you to calculate the ADC. Now, before we delve into the ADC, this is the brain, a complex organ responsible for controlling various functions of the body, and this is the T2 image, a type of MRI scan that provides detailed information about the brain structure. The restriction from this lesion, which is an area of abnormal tissue, affects the movement of water molecules within the brain tissue, so the signal will appear either bright or black, depending on the specific characteristics of the lesion. All right, here's the image. What will the ADC image be like? All right, in, in, in. How, according to this discussion, from the equation we were talking about earlier, can we derive the ratio of the signal intensity at P0 to the signal intensity at 1000 from the signal intensity at P0 using this equation in a detailed manner? It will start to give you the value for each voxel present and its brightness, as we have previously discussed. I told you it could be this, this, and this. So the ADC will show you that the existing choices have a constant, leading to something called. In this context, which is crucial to understand the underlying principles of this equation and its implications for our analysis in this study, as mentioned earlier in the discussion. There is something called a phenomenon known as shine-through, which is a consequence of having such an extended T2, because it has such an elongated T2. The magnetization in the transverse plane remains present even with all those gradients you applied. This still results ultimately in signal intensity coming from specifically within what we call here today the T2 characteristic feature of this particular tissue type under examination. It starts to give you quite an unexpected private signal even when using 1000 and P1100 settings respectively. So how do we differentiate between these two scenarios effectively? The one factor that differentiates them clearly enough for us scientifically speaking would be none other than our trusty ADC measurement tool. Indeed, yes, the ADC itself is precisely what can tell you whether it's truly just mere shine-through effect happening, or perhaps something else entirely different altogether. This is a T2 weighted image, and this is diffusion, and this is ADC. For example, here is a case of ischemia, and this lesion is present here, here, and here after 24 hours, and here after 7 days, and here after 30 to 60 days. For instance, you have a specific dot in this area, or there is a problem in it. In the case of diffusion, it will appear as a bright signal like this, right? The result is that there is restricted diffusion. The ADC will show from the equation that there is a black area in this case. I give a thermal plan to ensure that this is not shine through. Of course, after a certain time. Why did the signal here turn bright like this? Because after a certain time, it happens almost in the brain, and it gets like the fluids that disrupt the restrictions that were present. So it gives you the signal in this way, meaning it causes the signal to appear in the diffusion and more bright signal in T2, and the ADC shows a bright signal in this way. This is a long time after a significant period, 130 stereo, this is its range. Now let's look at the shine, for example. Here is another example. Here is a T2 weighted image, and here we have a lesion, and here is the side toxic around the lesion that exists. Here is a T1 weighted image. Now here is diffusion. This fluid here is considered fluid for me, or here is a black signal with a significant fluid. Here it is considered to have free motion, while this one is restricted in its diffusion, which gives you a more bright signal present in the ADC. On the contrary, the lesion gives you a black signal, while the one that had free motion for protons became bright. This is the diffusion weighted imaging, here in the case of shine-through. For example, T2 here has a lesion, and with diffusion weighted imaging, there is a bright signal. And with ADC, it appeared that there is a bright signal. And this is called shine through. The ADC, or apparent diffusion coefficient, is a crucial tool in the medical field, particularly when it comes to diagnosing conditions such as strokes. It assists healthcare professionals in distinguishing whether a patient's symptoms are due to a stroke or if they might be attributed to another cause entirely. When a stroke is present, the ADC will display specific patterns or changes that are indicative of this condition. These changes are critical for accurate diagnosis and subsequent treatment. Therefore, understanding how to interpret the ADC is essential for medical practitioners in providing the best care possible. If there is an increase in the diffusion weighted image, it appears in the ADC in this form, in the T2 shine throw. In the T2 shine throw, it will appear whether in diffusion or in ADC. There are many well-known examples. For instance, here is a lesion, and here with the diffusion weighted image, and here with the ADC. The difference is very clear, and here with the difference is indeed very clear. The same applies here in the case of stroke, also here in this area or in the lesion.